that construction helps in creating precise and accurate figures. Here in this section, we are going to learn about constructions. You are also expected to give the mathematical reasoning behind each construction. Remember, practice makes a man perfect. One can expertise in drawing these constructions only through practice. Now, let's move on to the topic. Tools required. We will need a protractor, a compass and a graduated scale. We need to know how to divide a line segment in a given ratio. Also, to construct a triangle similar to a given triangle as per the given scale factor. To construct the pair of tangents from an external point to a circle. Let's discuss the division of a line segment and we'll see its construction. If a line segment is given and you are asked to give it in the ratio say 3:2, how will you do it? You may do it by measuring the length and then marking a point on it that divides the given line segment in the ratio 3:2. But suppose if you don't have any way of measuring it precisely, how will you find it? Here we are going to see one way of finding such a point. Construction 1. Statement. To divide a line segment in a given ratio. Given a line segment AB, we want to divide it in the ratio m:2n, where m and n are positive integers. Here, let us divide the line segment AB in the ratio 3:2. Now, let's move on to the steps of construction. First one, draw a line segment AB. Second, draw any ray AX making an acute angle with AB. What is an acute angle? Angle less than 90 degree. Third step, mark 5 points. How we got 5? Which is equal to m plus n. Here 3:2. So, m plus n is equal to 5. So, mark 5 points A1, A2, A3, A4, A5 on AX such that A1 is equal to A1, A2 is equal to A2, A3 is equal to A3, A4 is equal to A4, A5 by drawing equal arcs. Now, join B, A5. Next step, since we want the ratio 3:2 through the point A3, that is our m is equal to 3, draw a line parallel to A5B by making an angle equal to angle A5B at A3, intersecting AB at the point C such that angle A5B is equal to angle A3C. Thus, AC is to CB is equal to 3:2. Let's see the justification. We need to prove C divides AB in the ratio 3:2. That is mathematically AC is to CB is equal to 3:2. Refer the figure. Since angle A5B is equal to angle A3C, so for lines A5B and A3C with AX as the transversal, we know the corresponding angles are equal. Therefore, A5BB parallel to A3C. Now, since A5B is parallel to A3C, by the basic proportionality theorem, we can write AA3 by A3A5 is equal to AC by CB, right? Now, by construction, AA3 by A3A5 is equal to 3 by 2. Therefore, AC by CB is equal to 3 by 2. This shows that C divides AB in the ratio 3:2, hence justified. Let's move on to the next construction, constructing a triangle similar to a given triangle. To construct a triangle similar to a given triangle as per given scale factor, there are two general cases. First case, triangle to be constructed is smaller than the given triangle. That is when the scale factor is less than 1. Second case, the triangle to be constructed is larger than the given triangle. For that case, scale factor is greater than 1. Now, what is the scale factor? scale factor means the ratio of the sides of the triangle to be constructed with the corresponding sides of the given triangle. That is, mathematically, scale factor is equal to side of to be constructed triangle divided by side of the given triangle. Now, let's move on to the construction, considering first the scale factor to be less than 1. Construction 2 statement. Example 1, scale factor less than 1. To construct a triangle similar to a given triangle ABC with its sides equal to 3 by 4 of the corresponding sides of the triangle ABC. That is, the scale factor is equal to 3 by 4. Given a triangle ABC with scale factor is equal to 3 by 4. Therefore, scale factor less than 1. We need to construct a triangle similar to triangle ABC. Let's see the steps of construction. First one, draw any ray BX making an acute angle with BC on the side opposite to the vertex A. Now, second step, mark 4. How we got that 4? The greater of 3 and 4 in 3 by 4 ratio. So, mark 4 points B1, B2, B3, B4 on BX such that B1 will be equal to B1, B2 will be equal to B2, B3 will be equal to B3, B4 by drawing equal arcs. Now, we need to join B4, C. Next step, draw a line through B3. How we got that B3? The third point, the 3 being smaller of 3 and 4 in the 3 by 4 ratio. So, it's draw parallel to B4C to intersect BC at C dash. Next step, draw a line through C dash parallel to the line CA to intersect BA at A dash. Thus, triangle A dash B C dash is the required triangle. Let's see the justification part. Refer figure. To prove, since scale factor is 3 by 4, we need to prove A dash B by AB is equal to A dash C dash by AC is equal to B C dash by BC is equal to 3 by 4. By construction, B C dash by BC is equal to BB3 by BB4, which is equal to 3 by 4. Mark it as equation number 1. Also, A dash C dash is parallel to AC. So, they will make the same angle with the line BC. Therefore, angle A dash C dash B is equal to angle ACB. What is the reason? They are the corresponding angles. Mark it as equation number 2. Now, consider triangle A dash B C dash and triangle ABC. Angle P equal to angle P. Reason? It's a common angle. Then, second, angle A dash C dash B is equal to angle ACB from equation number 2. Now, triangle A dash B C dash is similar to triangle ABC by AA similarity. What is AA similarity? Angle similarity. Now, since the corresponding sides of similar triangles are in the same ratio, we can say A dash B by AB is equal to A dash C dash by AC is equal to BC dash by BC. So, again we can write A dash B by AB is equal to A dash C dash by AC is equal to BC dash by BC is equal to 3 by 4 from equation number 1. Hence, justified. Next, we will see the second case when the scale factor is greater than 1. Construction 2 statement. Example 2, scale factor greater than 1. To construct a triangle similar to a given triangle ABC with its sides equal to 5 by 3 of the corresponding sides of the triangle ABC. That is, scale factor is equal to 5 by 3. Given a triangle ABC with scale factor is equal to 5 by 3. Therefore, scale factor is greater than 1. Now, we need to construct a triangle similar to triangle ABC. Let's see the steps of construction. First step, draw any ray BX making an acute angle with BC on the side opposite to the vertex A. Next step, Mark 5 points. How do we get 5? The greater of 5 and 3 in 5 by 3 ratio. That is B1, B2, B3, B4, B5 on Bx, such that B1 equal to B1, B2 is equal to B2, B3 is equal to B3, B4 is equal to B4, B5 by drawing equal arcs. Now we need to join B3, C. The third point, as 3 is smaller in 5 by 3. Now draw a line through B5 parallel to B3C to intersect BC extended at C dash. Next, draw a line through C dash parallel to the line CA to intersect BA extended at A dash. Thus, the triangle A dash BC dash is the required triangle. Let's move on to the justification part. Refer figure. To prove, since scale factor is 5 by 3, we need to prove A dash B by AB is equal to A dash C dash by AC is equal to BC dash by BC is equal to 5 by 3. By construction, we can say BC dash by BC is equal to BB5 by BB3 is equal to 5 by 3. Mark it as equation number 1. Also, A dash C dash is parallel to AC. So, they will make the same angle with the line BC. Again, we can write angle A dash C dash B is equal to angle ACB. Reason, they are the corresponding angles, and now mark this as equation number 2. Now, consider the triangles A dash B C dash and triangle ABC. Angle B equal to angle B, reason, they are the common angles. Now, from equation 2, we can say angle A dash C dash B is equal to angle ACB. Therefore, triangle A dash B C dash is similar to triangle ABC by AA similarity. What is AA similarity? It is angle similarity. Since the corresponding sides of similar triangles are in the same ratio, we can write A dash B by AB is equal to A dash C dash by AC is equal to B C dash by BC. Now, from equation 1, we can again write A dash B by AB is equal to A dash C dash by AC is equal to BC dash by BC is equal to 5 by 3. Hence, justified. Next, we will see the construction of tangents to a circle. To construct tangents to a circle, at first we need to consider the position of the point with respect to the circle. Position of the point can be inside the circle, on the circle or outside the circle. So, depending on the position of the point, the number of tangents that can be drawn can also vary. Let's see first the number of tangents possible for varying positions of the point. When point A lies inside the circle, no tangent can be drawn to the circle through this point. Now, when the point B lies on the circle, how many tangents can be drawn? Only one tangent can be drawn to the circle at this point, and it is perpendicular to the radius through this point. Now, when the point C lies outside the circle, what is the case? Two tangents can be drawn to the circle from this point, and the tangents are CP and CQ. Here, we shall see the third case, that is when the point lies outside the circle. So, construction 3 statement: to construct a pair of tangents to a circle from a point outside it. Given a circle with center O and a point P outside the circle. We need to draw tangents from point P to the circle. Steps of construction. First, join PO. Make the perpendicular bisector of PO. Let M be the midpoint of PO. Second step, taking M as center and MO as radius, draw a circle. Let it intersect the given circle at points Q and R. Third step, join PQ and PR. Then PQ and PR are the two required tangents. Let's move on to the justification part. Refer the figure. To prove, what we need to prove? We need to prove PQ and PR are the two tangents to the circle. So for that, join OQ and OR. Now, angle PQO is an angle in the semicircle of the blue circle. And we know that angle in a semicircle is a right angle. Therefore, angle PQO is equal to 90 degree, which implies OQ is perpendicular to PQ. Since OQ is the radius of the circle, PQ has to be the tangent of the circle. Reason, since tangent is perpendicular to radius. Similarly, PR is a tangent to the circle, hence justified. Note, how to construct tangents to a circle if suppose the center of the circle is not given. If the center of the circle is not given, we find the center first by taking any two non-parallel chords. Then what we have to do? Then find the point of intersection of their perpendicular bisectors. The point of intersection of these perpendicular bisector will give the center of the circle. Then you could proceed the same steps as we have done in the construction 3. So, let's have a recap of what we have learned in this section. We were dealing with some constructions. First one, division of a line segment in a given ratio. Second, constructing a triangle similar to a given triangle as per the given scale factor. We have considered two general cases with scale factor less than 1, where the triangle to be constructed is smaller than the given triangle, and the other case scale factor greater than 1, where the triangle to be constructed is larger than the given triangle. Also, we have seen the constructing a pair of tangents from an external point to a circle. We have seen that if the center is given, directly follow the steps of construction 3. If suppose the center not given, we have seen that we need to find the center first by taking any two non-parallel chords and then find the point of intersection of their perpendicular bisector, and the point of intersection of these perpendicular bisectors will give the center of the circle. Then follow the steps of construction 3.